Excellent. Our next speaker is Lindsay Dever from Millersville, who will talk about matrices.
Thank you. Thanks so much, Mel, for organizing and for allowing me to speak. Today I'm going to talk about some atoms that we discovered in the semigroup of non-negative integer matrices. And this is joint work with Ava Goodhart, Greg Heilbrunn, and Tony Wong. And I believe Greg is here, so feel free to chime in if Greg wants to chime in or if anyone has questions for Greg as well. Okay, so we're thinking about the question of when a matrix factors. And if you're factoring a matrix, you have to make sure you're in a setting where this is a meaningful question. So for example, if you have real matrices, this is a very uninteresting question because every matrix factors into just A times A inverse times your matrix. So this is not a good question. If you restrict to integer matrices, this is still an uninteresting question. So if you take your matrix, you can do any row or column operation and then just factor out that elementary row up matrix. So for example, here we're subtracting the second row from the first row and we can factor out that corresponding matrix. So this is still not a good setting for this. If you restrict to positive integer matrices, so all this 2 by 2, this does become an interesting question. Chuan and Chuan in the 80s looked at this setting and they classified the matrices that factor for determinants 1 and p. As far as I know, matrices with other determinants, I think this is still an open question. But let me know if anybody knows of any work in this area, but I don't think there has been any recent work. So another setting where this is an interesting question is non-negative integer matrices, so now allowing 0. So this was studied by Nicholas Bathe and his collaborators and students in 2011 and 2022 papers. So this is the setting I'll be talking about today. So first of all, I wanted to start with where this project started. So Nicholas Bathe was a professor at Franklin and Marshall who passed away, unfortunately, of cancer in 2021. So he had been working on this project with his students on matrix semigroups. And one of those students was Greg Heilbrunn. And so after Nick passed away, Ava took on Greg as her student and helped him complete his honors thesis. So Greg is now an alumni, but Ava reached out to me a couple of years ago and asked if I would like to join the project and continue working with Greg and Ava. So I'll be presenting on our work. And then we had presented a conjecture at a conference which Tony Wong proved. And so he is now on the paper as well. Okay. So let's talk a little bit about the math. So first of all, we have a semigroup. So a semigroup is a set with an associative operation that is also cancellative. In our setting, we do have an identity element, so we can talk about units. So units are just our elements that have inverses. So our non-negative integer matrices with determinant 0 form a semigroup with identity. And our units are the identity element or the exchange matrix, 0, 1, 1, 0, which exchanges the rows or columns. Okay. So when you talk about factorization, you're always talking about things up to associates. So for example, if I take my matrix and I multiply on the left by j, that exchanges the columns. If I multiply on the right, oh, vice versa, it exchanges the rows. If I multiply on the right by j, it exchanges your columns. And if I multiply on both sides, it exchanges both. So we think of factorization as up to associates, so we don't really think of these as different factorizations. Okay, so a matrix is an atom if it doesn't have any non-trivial factorizations. So it can only factor into something times the identity or the exchange. Factorization is not unique in this setting. So for example, 15, 10, 10, 15 has two, it may have more, but I have two different factorizations here. And both of these are actually factorizations into atoms. Um, and interestingly, they have different lengths of factorization. So length 2 and length 3. Um, and these don't factor any further. Okay, so what are the minimum requirements to be an atom? So first of all, your atom has to have relatively prime entries in each row and each column, because otherwise you can just factor out that number. So for example, here in the first row, we have a factor of 5, so we could just factor out that row operation matrix, and we can factor that out. So that is not an atom. We also say that a matrix is doubly balanced if, like, we don't have a row that's each entry is greater than or equal to the row below it. Um, and each column can't, like, each entry can't be greater than or equal to the element next to it. So this was terminology borrowed from a paper of Rainey. Um, so we are required to have everything doubly balanced because otherwise you can just subtract one row or column from the other. So for example, here, the first row is dominant over the second row. So we can subtract the second row from the first row and still have a non-negative matrix, and factor out 1, 1, 0, 1 when we subtract that out. Okay. All right. So, Baith and his students found some classes of atoms of this semigroup in their 2022 paper. So we have associates of 1101. We have associates of P001, where P is prime. And we have, for the third bullet point, this is matrices that are doubly balanced with our relatively prime adjacent entries, where the minimum value is 1, 2, or 3. So if we have one of those three values in our matrix, then we are an atom. Okay. Um, the fourth bullet point, they also showed a class of atoms where you have matrices, bisymmetric matrices, with entries x and x plus 1. Where the absolute value of your determinant, which is 2x plus 1, is prime. So they showed that these matrices, the bisymmetric ones with entries x and x plus 1, form a sub-semigroup, and then they found the atoms in that sub-semigroup. Okay, so what was unknown? So factorization status was still unknown for doubly balanced matrices that have relatively prime adjacent entries, and the minimum value is at least 4. And so our goal was to find new classes of atoms among these unknown matrices. So today I'm going to talk to you about 4 different classes of atoms that we found in our work. Okay, so the first result came from work that Greg did in his thesis. So he showed that if you have a doubly balanced matrix with relatively prime adjacent entries, if it has absolute determinant P, 2P, or 4P, where P is prime, then that is an atom. So for example, this matrix has determinant 58, which is twice the prime, and so that is automatically an atom. So the idea of the proof is that if you factor a doubly balanced matrix with relatively prime entries, the first and last factor are also doubly balanced with relatively prime entries. And Greg showed that the determinant of those cannot be 1, 2, or 4. And since determinants are multiplicative, then you can't have 1P, 2P, or 4P, essentially. Okay. All right, so next we proved some upper bounds that gave us additional classes of atoms. So along the way, we proved this nice little lemma, and since it's the end of the day after a long week, I wanted to show you the proof of the lemma because it is very fun and cute and easy to understand. So hopefully it will be a nice break. So if we have a matrix that is doubly balanced with relatively prime entries, if it factors into A times B, we showed that A and B do not have any zero entries. So the idea here is pretty simple. So we just assume we have a zero entry. So for example, in the upper left corner of our first factor, then if we multiply those two matrices, we have in the first row B times G and B times H. Okay, so we have a factor of B in the first row, but we're assuming that has relatively prime entries, and so B has to be 1, otherwise there's a common factor. All right, so we replace our B with a 1, we multiply our matrices together, but now we have G and H in our first row, and something in our second row that looks kind of big, which is not good because we want our matrix to be doubly balanced. So the only way to make this matrix doubly balanced is if D is 0. Um, so we plug in 0 for D, multiply them together, but now we have a common factor of C. So these now share a common factor. So C has to be 1. So essentially, you're getting that the first matrix is the exchange matrix. And you can similarly plug in zeros. If you plug in zeros anywhere else, you'll get either the identity or the exchange matrix. Okay, so that was one of the ingredients in our upper bounds. So we showed these upper bounds on factorable matrices. So if X here is not an atom, then it has to satisfy these upper bounds where the off-diagonal entries X and Y are bounded by 2 times Z minus 1 times W minus 1, and the diagonal entries W and Z are bounded by 2 times X minus 1 times Y minus 1. So essentially, the diagonal entries can't be too large compared to the off-diagonal entries and vice versa. So for example, if we have 5, 11, 51, 7, if this factored, we would have the inequality that 51 would have to be less than or equal to 2 times 5 minus 1 times 7 minus 1, which is 48. And that is obviously not true, which means that X has to be an atom. Okay, so we also specialize to bisymmetric matrices. So if you just put these bisymmetric matrices into here. So we do have to assume that X and Y are relatively prime. Otherwise, we could pull out a factor. But we showed that if X is not an atom, then it must satisfy these bounds. So X is bounded by twice Y minus 1 squared. So the nice thing about these bounds is if you pick a fixed X, like let's just say X is 5, then there's only finitely many Y's that can satisfy this. So the idea here was we fixed certain minimum values, and then we essentially said, well, we can just go to a computer and algorithmically check if certain X and Y pairs will factor. And so we did that and looked at their factorizations. And keep in mind, this is still factorization in M2 of N0. So it's still over the group or the semigroup of all non-negative integer matrices. But we looked at the factorizations and essentially found all of the factorable matrices with this relatively prime condition for each minimum value. So for example, for minimum value 4, the only bisymmetric matrix with relatively prime entries that factors is 4, 5, 5, 4. All of the rest, where Y is relatively prime to 4, are atoms. Okay, so these are a complete list. So we looked at different factorizations, and we noticed that all of the factors were also bisymmetric. And this was very strange because we were looking over any matrix factorization. Um, and matrices that multiply to bisymmetric matrices like have no reason to be bisymmetric themselves. Um, but once we looked at like tens of thousands of matrices and all of them only factored into other bisymmetric matrices, this became a conjecture um, that if we have a bisymmetric matrix with relatively prime entries, if it factors, then both factors have to be bisymmetric. I did not believe this at first, but the algorithm doesn't lie, and it seemed to be true. Um, so keep in mind that it's necessary for these entries to be relatively prime. So for example, here, 15, 10, 10, 15 factors into these two matrices, which are not bisymmetric. Um, and this was very surprising to me that this couldn't happen if the entries were relatively prime. So here we have a common factor of 5, and this factorization does not appear to have anything to do with there being a 5 that can be pulled out of a row or column. Um, in fact, both of these matrices here are atoms because their minimum entry is 1 and they're doubly balanced. So it was totally unclear to me why this would be true, but it did seem to be true. So we presented this conjecture at a regional conference, so the EPIDEL conference. And 3 days later, Tony Wong emailed me and said, "Hey, I think I have a proof of your conjecture." And so our conjecture became a theorem. And Tony joined us on the paper and showed that if a bisymmetric matrix of this kind factors, that the factors are also bisymmetric. Okay, so once we know this, we could improve our algorithm a lot. So our original algorithm ran for like several months. Um, and the new algorithm, where you know the factors are bisymmetric, um, like maxed out of the amount of data I was willing to fill within like less than a day, I think. So this was much more efficient now that you know the factors are bisymmetric. And so we were able to find all of the factorizations of matrices with minimum up to 4,000. And so because of our upper bounds, we know that all other bisymmetric matrices with minimum up to 4,000 that have relatively prime entries aren't necessarily atoms. So this is a complete list of um, factorable matrices up to that minimum where you have relatively prime entries. Okay, so we have 128 million factorizations. I could not fit them all on the slide, so I have a link to our data sets if anybody is interested in playing around with them. You can also just reproduce it with the Python. The Python code is also posted here. Okay, so once we knew that bisymmetric matrices could only factor into other bisymmetric matrices, Tony was able to prove a tighter upper bound for bisymmetric matrices that if they are not atoms, they must satisfy this tighter bound. And he did, in fact, show that this bound is tight, so it can be achieved. Okay, so in summary, we found 4 classes of atoms. So all of these doubly balanced with relatively prime entries. So our classes of atoms were our matrices with determinant P, 2P, and 4P, where P is prime. We have matrices that violate one of our upper bounds. We have bisymmetric matrices that violate this tighter upper bound. and we have the bisymmetric matrices with minimum up to 4,000 that do not appear in our factorization list. Okay, so I wanted to talk about some possible future directions that people could go in because this is a relatively unexplored area with, I think, a lot of opportunities for future questions. So first of all, I think the positive integer matrices are a very unexplored area. And so I think there's a lot of work to be done looking for atoms in the semigroup of positive integer matrices. There's a lot of, if you like coding, there's a lot of interesting things to look at in the coding to explore different factorizations, for example, of non-bisymmetric matrices. There's a lot of interesting number theory questions. So, for example, if you look at, where's our data? If you look at the X and Y values that appear, can you tighten some of those upper bounds on the Y for certain equivalence classes? So Tony had noticed some opportunities for some tighter upper bounds for certain equivalence classes of X. So that could be an area if anybody is interested. Tony had some ideas of where that could go. And finally, I know I didn't talk about combinatorial applications, but I think there's a lot of room for combinatorial questions in this work. So thinking about how many matrices are atoms. So for example, if we fix an X for which Y or how many Y are those matrices atoms. You can also think about the number of factorizations, different factorization lengths. There's all kinds of different combinatorial questions that I think could be explored in this area. Okay, so I will stop there. I have links to our preprint on the archive and factorization data, and feel free to email me or speak up if you have any thoughts or questions.
Oh, thank you very much. Uh, are there any questions for Lindsay?
So if you consider just integer matrices without positivity, then as far as I understand, uh, atoms here are precisely the matrices uh, with determinant plus minus p, right?
No. So, um, oh, you mean in the positive integer setting?
No, just integers without the positivity at all.
Just like in general?
Mm-hmm.
Oh, I see. So you're saying there are certain classes. Can you?
So if you just consider
Mm-hmm.
matrices with integer entries of any size, then as far as I understand, atoms are the matrices with determinant plus minus prime. This
Okay.
corresponds to a very simple object because
Mm-hmm.
you can to every matrix you can associate a z module, and you can factor Zn by this submodule of Zn, and you get an atom if and only if this group is a simple abelian group, right?
Okay.
So the question uh, is there any object like this for positive integer matrices or for non-negative
Hmm.
integer matrices? So can we associate something like modules?
Um, I'm
And
not aware of that. I'd be interested to kind of see what people have already thought about as far as integer matrices. We So as far as I know, Greg, correct me if I'm wrong here, but I believe Greg's result on the prime determinants only goes in one direction. So if its determinant is P2P or 4P, then it's an atom. But I believe we had examples where the determinants were prime and it they were not atoms.
Yeah, of course,
Yeah.
but still, maybe there is some object here, like
Hmm.
a abelian group, but with some additional structure. Maybe an abelian group, but with order or something like this.
Yeah, I don't know. If you have any ideas, feel free to email me and yeah. I'm not an algebra person. I kind of came from analytic number theory and then sort of jumped into this project a couple years ago. So if there's any more algebraic
Yeah.
things I'm missing, I would love to learn more.
Okay, thank you.
Okay, if there are no other questions, I thank all of our speakers again. If anyone is curious, by the way, about how scheduling works, um, why some people speak in the morning and why some people speak in the afternoon, the answer is very simple. Uh, if you live in Asia, Africa, or
Mm.
Europe, you speak in the morning. And the later in the day it gets, it's harder for people in those areas to stay up. So
That makes
people
sense.
in the uh,
Yeah,
what are
it's
they?
almost midnight in Moscow.
Yeah, exactly.
Wow.
I mean, it's especially in Australia, Africa. Yes. Anyway, that's the story. So the later in the day, the more likely you are to be speaking. If the later in the day you're speaking, the more likely you are to be in America.
Yeah.
Anyway, thank you all. For anyone who wakes up early, our first speaker tomorrow morning is in Japan, and that person gets to speak at 7:30 a.m. In Eastern Daylight Time. Uh, Bye all. Good night.
Hi, thank you.
Lindsay, your structure is a semi-range.